my name is Julie. I'm the product manager for Unreal Engine, and I helped kickstart the Fortnite mobile project. So here at Epic, eating our own dog food is super important to battle test the features that we develop for Engine. Developing a feature is one thing, but getting it through the production process and shipping a game with it is a whole other endeavor. Last year with Battle Breakers, we introduced several improvements and features for mobile. For example, you can find out more about how we implemented chunk downloading on Ben Ziegler's recent blog post. And as devices are getting more and more powerful, we know that the technology is there to deliver full mobile gaming experiences. Tim mentioned this morning, this all started in Korea a few years ago, and recently with games like Lineage 2 Revolution. But until recently, we hadn't had really any proof points that there was an appetite for this type of experience in the West. So last fall, when we started thinking about putting Fortnite on phones, for us it was a great opportunity to further improve the experience of developing mobile games in UE4. And our dev team was able to get the game stood up on high-end devices without adapting to Touch UI in about 10 days. So that speaks to the versatility of the engine. And initially, we started evaluating how to do a traditional mobile port of Fortnite. Do we create a different map with a different content team? Do we import the same map, but reduce the density or the quality of the assets? Do we take the same map and just cut up a smaller portion of the map? But the amazing thing about Fortnite is not just that people love to play the game, but how it's become a really social experience. We're hearing about people playing with their real-life friends, their brothers, their sisters, and even their parents. So in a way, it made perfect sense for the mobile version to be the same game and allow crossplay with other platforms. Because with that, you could play Fortnite wherever you want, whenever you want, with all of your friends, no matter what platform or device they're playing on. But from a technical point of view, this posed a few interesting challenges. So in addition to making it fun to play with touch controls, we had two major technical challenges. One of them is the challenge of optimizing content with a single content pipeline, while the PC team was implementing level streaming, and while the PC console team was busy adding even more stuff to the map with the Map 2.0 update. Jordan and Ryan will come talk a little bit more about that later. And the second major technical challenge was how do we get it to fit in memory and running with good performance? So I'd like to introduce, back to the stage, Nick Penwarden to talk about that.
Thank you, Julie. So thanks, everybody, for coming to the second part of our talk on optimizing Fortnite, specifically how we brought Fortnite Battle Royale to mobile devices. So as Julie mentioned, we set out with the idea of having one game on all platforms. We want to support crossplay, and therefore, we had a number of constraints. We had to use the same map. Anything that affects gameplay has to be supported, whether it's something like an effect showing a pickup, or particularly the engagement distance. So we can't drop meshes out that a player can hide behind, basically. Our approach was to use scalability to try to run the same content on all platforms. One benefit of taking this approach is that all of the optimizations that we make to run on mobile ended up helping both low-end PC and our 60 FPS console effort, and vice versa. So we ended up with a good amount of synergy between the two. I'm going to talk about optimization, but again, as Julie mentioned, there are a lot of other really interesting challenges with getting Fortnite Battle Royale experience onto mobile devices. The visual indicators for footsteps and gunshots, since you might not be able to listen to sound on your phone, and so on. So here's an image of the Lonely Lodge running on PC at high settings. And as we kick in scalability, here's on PC at medium settings. And there's the same location running on an iPhone 8 Plus on iOS using our, these are the highest scalability settings for mobile. So as you can see, we're able to faithfully represent the game on mobile devices with a couple of concessions in terms of number of triangles and texture resolution. From a rendering feature perspective, Fortnite uses a number of features that we support on PC and console. Things like cascaded shadow maps and ray trace distance field shadows, distance field ambient occlusion, volumetric fog, light shafts, dynamic lighting and dynamic shadows, physically based materials, and temporal anti-aliasing. On mobile, we support a subset of these features. So what we had to do was figure out how to make the content, again, look faithful while with the subset of features that we support. But the main features we do a support for, such as cascaded shadow maps for the sun, physically based material approximation, GPU particles, and so on. So let's talk a little bit about our approach to scalability. In order to get running at 60 frames on consoles, as well as playable on mobile devices, we needed as many knobs as we could to try to get the experience running great on every device. In UE4, we have a couple of different systems for this. So we have scalability groups, and these are intended for settings that can change at runtime. So for instance, here you can see some of the foliage quality settings at different levels, in this case on iOS. So at low settings, there's no foliage at all. At medium settings, density scale is bumped up to 0.2, and at high settings, 0.75. Groups can be overridden per platform, so these foliage settings are different on iOS and on Android and on Xbox and on PC. And some of these settings are general engine features that you can use in your games. Some are specific to Fortnite. So fort.scalability.ai budget, for instance, is specific to Fortnite gameplay code. It doesn't really make sense as an engine feature. But similarly, any scalability that you add to your game exposed as a console variable, you can easily incorporate into the scalability system. On top of scalability, we have something called device profiles. Basically, the engine on boot will figure out which device you're running on and can set up INI values based on that hardware. So here, when you're running on an iPhone 10, we first apply all of the settings in the iPhone 10 device profile, and then we follow up a hierarchy. So the iPhone 10 gets the iOS high spec, so it sets the scalability values. And then we have some settings that we use across all iOS devices and across all mobile devices. Memory scalability is a little interesting. The amount of memory that a device has doesn't always correlate with its performance. So if we just nerfed memory across the board on low-end devices, that may actually be the wrong trade-off. So in device profiles, we support the concept of different groups for different buckets of memory. So for instance, the iPhone 8 has 2 GB of memory, but it's very fast relative to other phones. So let's talk about when we started. Again, the game was built for PC and console, so getting it to squeeze down onto mobile was a bit of an effort. We started by seeing how it would run on a 4 GB device, and we ran out of memory, as you might expect. So let's talk about memory. On iOS, we allow ourselves about 700 megabytes of memory per gigabyte of physical memory. This way, if we use any more than that, then the OS might evict us for using too many resources. On Android, the memory situation is much more complicated, depends a lot on the device. Talking with partners, the general recommendation they have is if they're going to ship on a 2 GB device, we need to target less than 500 megabyte. We found that on 3 GB devices, if we stuck to the 1.4 GB number that we did for 2 gig iPhones, it mostly worked. We did a lot of memory optimization. A lot of this is content, and some of it was adding new functionality into the engine that allowed our content team to go and do their work. So again, some are just straight up optimizations using 2 byte per character strings instead of 4 bytes on iOS. Some was using ASTC texture compression and optimizing for size rather than quality in most cases. Adjusting the texture streaming pool. We added the concept of a per platform minimum LOD. So an artist can go to a mesh and say, on a particular platform, whether it's iOS or Android or Xbox, I want to always render with at least LOD1, never show LOD0, and then we just cook that out of the build. So we never load it into memory, we never even ship it. And similar with materials, we support low, medium, and high quality variants based on material quality switch, and we just cook out everything except for low quality variants on mobile in order to save memory. A number of new audio settings per platform, so some automatic variation culling, per platform downsampling options, and I think I actually have some information about that later on. On the collision side of things, one big optimization was just going through the map and making sure that we don't enable collision on sections where it's not needed, as well as using LODs for collision. A lot of the meshes initially didn't have LODs, so as the artist went in and added LODs, they were able to use this feature to use LODs for collision, and in some cases reduce the number of collision polys drastically. I mentioned audio, so in terms of variation, our sound design team added a number of variations for things like gunshots or when you're hitting a wooden wall or a concrete wall. And so we added the ability to say, we want to limit the number of variations on a particular platform to 3 or to 4. This way, we could automatically cull across the board and get ourselves closer to our memory budget. And then we also added a quality level node so that our sound designers can go in and make better trade-offs where they think they're really needed. We also supported per platform quality settings. So in this case, we can downsample sounds based on the platform. We can change the compression quality settings. And we can also change the threshold for real-time decompression. This is a memory and performance trade-off. It's basically how do we want to decompress on load and just keep the thing in memory, and then when we want to play it, we don't have to decompress it in real time, or do we decompress it in real time and potentially add a little bit of latency before the sound plays? Depending on how much memory you want to save, you might want to make different trade-offs. So let's talk about optimization. We wanted players at the end of the day to experience 30 frames per second at the highest visual fidelity possible. However, on a mobile device, maxing out the CPU and GPU generates heat, which causes the phone to downclock, which means now you're no longer at frame rate. Plus, it's also really uncomfortable to play on a phone that feels like it's been sitting in the sun for 3 hours. So to that end, what we ended up doing is we actually target 60 frames per second for the environment, but we vsync at 30 frames per second. This ended up being a good trade-off for us in that when the action starts to heat up, we can start to max out the phone, absorb the additional performance that we need to make the game run well. And then when things settle down and you're back to just running around the environment or waiting, then the device is able to cool down because we're basically running at 60, but letting the phone idle for about half the time. So let's talk a little bit about how we track this. So when we started, this is actually a data capture from early February. We added a quick command to Fortnite called Profile Go, where we could just hop around to the different POIs in the map. So City Overlook is on a cliff overlooking Tilted Towers. Greasy Grove and Fatal Fields are both POIs in the game. Woods is Wailing Woods. And we use this to track the environment performance as we went through and made optimizations. So here we track things like the total number of draw calls, the frame time, and the game thread and render thread times. Obviously, when we started, or we were actually midway through the process here back in February, we still had a long way to go. We also use this for identifying perf regressions and validating optimizations. It allowed us to do things like run experiments in isolation. This is data from the build that we shipped on iOS. So you can see we're actually finally able to hit our frame rate targets of around 60 FPS for the environment. In terms of experiments, as an example, we plan to ship with MSAA enabled across the board in 3.4, and we did this by, we basically enabled MSAA. We could run this pass and see exactly what effects it has on frame time and see that we still maintain our frame time budgets. Similar to how we handled 60 frames per second console, we also had QA capture profiles and stats during our daily playtests. We use these to identify optimization targets, causes of hitches, et cetera. So again, this is actually from a playtest just a couple weeks ago before we were shipping. And so hitches per minute is basically how many, that's exactly what it sounds like, how many times we hitch per minute. Our threshold there is 60 milliseconds. MVP 30 is the number of frames that we dropped. since we're vsyncing at 30, and then average frame times. So for example, when we're talking about hitches, we had a particular hitch in Fortnite game code where as levels streamed in, we would actually need to go and create a dynamic texture to track which pieces of the building are destroyed or not. Ryan Brooks will actually talk a little bit more about that later on. But the code that was doing this was actually flushing the rendering thread and causing a massive hitch. So this is just an example of, we got one of these profiles back from a playtest, looked into it, and could easily turn this around and get this fixed for the next playtest. I want to talk a little bit about threading on mobile. So in most iOS devices, we have 2 cores. So we use the traditional sort of game and render thread split that we've had in Unreal for a long time now, and we have one task thread running for async tasks. Mostly this is for level streaming, so we use it to keep I/O going. Basically, while both the renderer and the game are idle, the async task thread goes and just handles level streaming for us. On newer devices like the iPhone 8 and iPhone 10, we have 2 fast and 4 efficient cores. So what we do is we add 3 more task threads. We do things like parallel animation evaluation, particle simulation, physics, async scene queries, texture streaming, and so on. We also add a dedicated audio thread, and this allows phones like the 8 and 10 to both stream faster as well as handle higher spikes of performance requirements. Actually, coming back to this, I did want to point out again, looking at this, you'll see a lot of idle time, and that's by design. That's not an accident. That's not us failing to completely fill the phone with tasks. We are intentionally trying to leave those cores idle because we do not want to max out the device. Otherwise, we're just going to drain the battery and heat the thing up. And then when we really need that performance, we're not going to have it available. On Android, the situation is a little more complicated. We're relying on phones that have at least 4 cores, usually 2 big and 2 little. We add an RHI thread for submitting OpenGL commands. So this is part of the parallel rendering support in UE4. Basically, it's a thread that all it does is submit commands to OpenGL. This was a big win for us since we can overlap it with the rest of the rendering work and everything else that we have going on. As you can see, this is from a Galaxy S8, and you can see we are 100% bound on submitting OpenGL commands in Fortnite. So moving on to CPU rendering costs. 2 main rendering costs that we need to look at. The first is scene traversal. So this is something that scales with the total number of meshes in the world, culling, relevancy, and so on. Level streaming mostly solved this for us. It basically gets a large portion of the world completely out of memory. The renderer doesn't have to consider it, and so we don't spend any CPU time on it. The rest all came down to draw calls, which was our main bottleneck when it came to rendering. Just wanted to point out, this is a little bit more than just the draw index primitive call itself. It also depends how much state you're setting between draw calls. So if you have one material and one mesh that's instanced 100 times throughout the world, that's far cheaper than 100 unique meshes with unique materials. So this became relevant for content optimization. On consoles, we can see up to 35, or on PC, 4,500 or more per frame. On mobile, we can't afford nearly that much. So on iOS and Android, just like looking in terms of the number of draw calls we can support, after our optimizations, this is where we are right now. City Overlook is the stress test for draw calls, the best one that we have. Again, it's a cliff overlooking Tilted Towers. And City Streets is down in Tilted Towers itself, so it's a little bit more of an average case in Fortnite. On iPhone 8 Plus and even 7 Plus, sort of the mid-range of iOS for us, CPU time is pretty good. It's well within the 16.7 milliseconds that we're targeting. In this case, the numbers I'm showing are not the total render thread time. This is purely the amount of time that we're spending submitting draw calls for base pass and for occlusion. On Android, the CPU time is entirely the time spent submitting OpenGL commands, and remains our largest bottleneck by far. So in terms of reducing draw calls, aggressive distance culling was a big important optimization. We cut a lot of decorative objects that don't impact gameplay, or we just drop them out very close to the camera. We also use occlusion culling to draw only what can be seen, and hierarchical LOD was the biggest optimization for us. For occlusion culling, we use hardware occlusion. We use that on every other platform. It just required a little tweaking to get good results on mobile devices. First, we had to add an additional frame of latency because on PC and console with the deferred renderer, we render the prepass and then we immediately issue occlusion queries. And rendering the prepass doesn't actually take that much GPU time, so the amount of latency before the GPU has results available for us is pretty small. We can count on that being available when we go to render the next frame. On mobile devices, it's not the case at all. We only render the scene once, there is no prepass, and that takes most of the frame. Therefore, we can't just wait for that immediately. We have to wait potentially 2 frames. On Android, it's running it's more like half a frame behind, but it's running a bit behind because everything is going through the RHI thread to submit to OpenGL. And so we account for a potential additional frame of latency. We also had to work around a couple of driver bugs that we found on Android devices where the number of queries were limited, and so we sort of virtualized them at the high level and flush wherever we need to. It's worth pointing out that the frame of latency, it's not a requirement. Basically, if the queries are ready, we'll read them. So sometimes, in certain situations, they will be ready and we can read them back. So if we're render thread bound and not GPU bound, that latency goes away. In cases where we are GPU bound, we do have that latency. Hierarchical LOD, as I said, was the biggest optimization for us. For things very far in the distance, we used the sort of traditional UE4 HLOD tools with simply gone to generate proxy meshes. These turn tilted towers from several thousands of draw calls into 7 draw calls. And when you see it from 2 kilometers away, it looks great. But we couldn't use it closer, partly because it doesn't look great, but also because we can't change engagement distance. To illustrate it, here is that city overlook location I was talking about earlier, looking over tilted towers. This is without any hierarchical LOD, showing all of the base meshes. And this is all rendered on an iPhone 8. And here it is using the HLODs. So of course it looks pretty ugly, but also you can see some of the windows just go away because you can't see them from 2 kilometers away, but you sure can see them here. And I might want to snipe someone in one of those buildings who's behind one of those windows. So we created something that we call Destructible HLOD. It's basically another chain in the HLOD, or another LOD in the HLOD chain, where we merge all the lowest LOD meshes together, create a texture atlas for it, and we can draw it in one draw call, and we have a little bit of tech art to be able to take those meshes and collapse them down to nothing. That way we can still not render a particular wall if it's actually meant to be destroyed, and I should be able to see a player behind it. Ryan Brooks will talk about that in more detail later on. So again, tilted towers, no HLOD. And here, oh, wait, back. This is actually with the destructible HLOD. And this is without LOD. So you can see actually from a visual perspective, they're reasonably good. And anywhere where I can see into the building, I can still see into the building. So this way, we have a way to reduce draw calls massively without affecting gameplay. As we shipped, this is what it looks like. So we actually, most are replaced with the HLOD, but the 2 nearest buildings you see are not. So I think we swap at right around 50 meters. Talk a little bit about GPU optimization. GPU was the easiest for us to tune with scalability settings. We can do things like reduce anisotropic filtering, which is a pretty big win on mid and low-end devices. We can tune terrain tessellation to reduce the number of triangles that we're drawing for the terrain and stuff like that. Resolution, we can tune the back buffer resolution, which is basically what the UI renders at, and we can render 3D separately at a lower resolution and upscale it before rendering the UI. We did prefer scaling the back buffer where possible because the upscale before rendering UI does cost us something. We only had to scale 3D separately on the iPhone 6s, where we needed to render the UI at full resolution, otherwise it just didn't look good. And so we scaled 3D separately instead. Foliage scaling, so we can control the density and the distance at which we control foliage via scalability. And so it was very easy to just turn foliage off on low memory devices and disable shadow casting. Any foliage that was big enough that it needed to be rendered for gameplay purposes, the artist can actually go in and tag those meshes as this one can't be removed by scalability. And we will render those out all the way to engagement distance, which is about 275 or 300 meters. Material quality. So we support material quality switches in the materials where artists can go in and make cheaper variations of materials. On mobile, we always use the low variant, and this allowed artists to simplify or remove vertex animation, as well as reducing pixel costs. We could have also used a feature level switch to specifically say this is intended for mobile, but we chose not to because we wanted all of the work that we were doing to potentially help out low-end PC users as well. On the shadow front, dynamic shadows have a large impact on both GPU and CPU performance. So on low, we simply don't render shadows whatsoever. On mid-range, we render one shadow cascade, and on high, we support 2 cascades. We tuned it so that generally if you're in a building and shadows are enabled, the entire building will be in shadow. But unfortunately, we couldn't support it on all devices. Here's just a massive list of some of the mobile improvements that will be coming in 420 as a result of us getting Fortnite up and running. There's a lot of work that we put into this, and I'm really excited that we're going to get to share it with everybody developing on Unreal. And with that, I'd like to introduce Jordan Walker to talk about how our art and content department dealt with scaling the game down. Thank you.
Thanks. Hi, everyone. I'm Jordan Walker. I'm a lead artist at Epic Games. I'm going to talk about how we crammed all this content onto a phone. So, like we've mentioned earlier, Fortnite Battle Royale presents some unique content challenges for optimization. 100 players in a match shooting, building, and destroying. It's a dynamic, large, open world built from small pieces. We want to have the same content on all platforms so that we can update the game together. Lastly, it's a PvP game, and we want to maintain competitive information to the players. We don't want anybody on a specific platform getting information that other people don't have. So, with our goals of 60 frames per second on console, improving min-spec performance, and launching on mobile, we share optimizations. We want to reduce draw calls, reduce triangle count, reduce instruction costs in the vertex and pixel shader, and reduce memory. Our content strategy relied on reports from engineers and tech artists. Profile Go provided consistent conditions for these reports, so it'd be the same type of day, in the same location, and we also had screenshots so that we could catch visual regressions. We used object list to track our memory usage. This helped us track down the biggest offenders and where to target our optimizations. We also had list textures. This lets us track our texture usage by texture name, the asset size, what size it was in memory, and whether it's not streaming. Below in this image, you can see where we generate a summary of all the vertices spent in the project. We're able to see the change since the last report and the percentage of change. This is important because we're constantly adding content to Fortnite, and we need to know when something has regressed in memory. And I can't emphasize enough, we had to dig into memory on meshes a ton just to make sure that we didn't have meshes that were too heavy and have too many verts, causing us just too much memory we're spending. So for character optimization, the first thing that we did was we combined material sections. So the eye shader is also part of the head shader now. We also removed unused sections. Fortnite's a game that's been in development for a while, and when we switched the character models to being used in Fortnite Battle Royale, there was some sections that they didn't need, like grenades off the waist of the character, and so they were assigned an invisible material. Now that we tried to get on lower spec platforms, we went through those meshes, removed those unused sections to remove our draw call count. So in the end, our characters have 4 sections: the head, the body, the backpack, and their weapon. Our characters have 4 LODs and 3 for weapons. We have a bake pose for LODs without facial bones. Here in LOD 1, you can see that there's a pose actually baked into the character. This is because we didn't want that character to look too neutral once we removed those facial bones. For mobile, we use LOD 1 as our min LOD. So that means we essentially just cook out LOD 0 on the mobile platform. And our character LODs range from around 30,000 triangles for LOD 0 down to 300 triangles for the lowest quality LOD. So in UE4, we have a new asset that lets us define our LOD settings. And this is an image just kind of giving you an idea of how that works. In Fortnite, we decided that LOD 1 will remove facial bones. LOD 2 will remove finger and twist bones. And the nice thing about this asset is you plug it into all of your skeletal meshes, and you're able to make broad, sweeping changes to the entire project just by tweaking one LOD asset. And this is important when you're trying to find that balance between visual quality and how much performance you're giving up or how much memory. When it comes to animations for characters, we had to take a look at a few long, detailed animations that were being used. An example was we had directional slides for the characters that were long and had a lot of noise built into them. So what we transitioned to was using a directional pose for the slides, and we had an additive noise on top of that. We switched our character materials from being masked to opaque. To add variation in skins, artists were painting, they were masking out various parts of the character, like pouches or straps, when they didn't want to have them displayed on the character. And this gives overdraw. The overdraw of that material has a performance cost on mobile. So what we did was we baked vertex colors into those attachments, and then we used the vertex shader to scale those verts down when they're not in use. And this allows us to have an opaque shader run on these character models. For the project, we disabled point light and spotlight shaders to reduce shader permutations, which costs memory. In the front-end screen, we have a lot of spotlights to give a cinematic look for our characters. So tech artists had to create a blueprint that basically says, am I running on low quality or am I running on mobile? And if so, let's turn on the directional light and swap out the skylight for something that works better for that platform. For effects, we started using explicit detail modes. In the past, our detail modes were inclusive. That means that anything in low detail mode, medium detail, would also appear in high detail mode. We wanted to be more targeted with the optimizations that we were making, and that's why we switched to explicit detail modes. This means that we can have an emitter that only shows up in low quality on mobile and doesn't affect any other platform. We also had to remove morph target meshes from effects. This is because those morph target meshes cannot be LOD'd, and the textures that define the morph were non-streaming uncompressed textures. Both of these are attributes that did not play nicely with our goal of trying to reduce memory across the platform. We also implemented significance settings for effects. I believe James talked about our significance manager earlier. What this allows the game to do is say, when there's a lot of combat going on and the performance is starting to lower, we can turn off effects that have low significance. We also enabled fixed bounds for as many particles that it made sense to do so for. This allows the game to call those particle systems more accurately. For effects materials, we switched to per vertex or non-directional lighting. Previously, we had been using per pixel lighting for our effects materials, but we were able to make the switch without much of a quality loss. We also consolidated our effects materials and utilized switches. Previously, there had been a few materials that looked similar or were doing similar effects, but the more materials you have, the more shader permutations you have, which is more memory. So we were able to consolidate these and implement a few switches that let us change those materials. We also disabled environmental effects on the mobile platform. One of the optimizations we had to take a look at was we had a few actors in the world that had a lot of components to them. An example here is the weapons that are dropped in the world. In the beginning, they had a few components. One was the weapon model. It had a translucent sheet behind that model, and also had a particle system adding some glowing rays. And lastly, it had a duplicate of that weapon model to do an outline effect on the weapon so it stood out in the world. So we combined the particle effect into the translucent shader using vertex shaders and just some shader math. And then we removed the duplicate of the weapon model and implemented that outline in the translucent sheet. So we're able to go from 4 components per weapon pickup down to 2. And that was a nice optimization to have. We also removed unused static switches from materials. Fortnite's been in development for a few years, and there's been features that have come and gone, and things that artists have tried that we're not using anymore. And we had to go through each material carefully and remove switches that weren't being used, because those switches were adding shader permutations to our project. We also used fully rough materials on mobile. This isn't for every material, and it's driven by the artist. They were able to target materials and say, on mobile, I want this material to have a roughness of 1, and that allows it to use a much faster shader path when being rendered. We also disabled post-process materials on the mobile platform. These were being used to do outlines around treasure chests and walls that the player could select. We re-implemented that in the pixel shader for those objects on mobile. When it came to textures, the first thing that we looked at when we dump out list textures is what textures are set to never stream. This means that these textures will essentially eat up a block of memory and will never MIP down. So you have to assume that you're always going to have to deal with that chunk of memory. We try to make that list of textures as small as possible and things that absolutely have to be set to never stream. We also gave some UI textures MIP maps so that they could scale down on different platforms. And then we moved on to generic texture optimizations, reducing the size of textures that are just too big and don't need to be. And we also consolidated similar textures. So an example would be we had a few tree textures that looked similar but with slight variation, consolidated that down to 1 texture, and re-implemented that effect using the shader to add variation. We also had our tech artists prioritize texture groups per platform using device profiles. So that's where our tech artists can say, okay, on this platform, I want character normal maps to be this size, and I want their color maps to be a smaller size. And we tweak that per platform based on what looks best for that device and what our memory needs are. For the project, we adjusted how view distance scale is set per platform. Normally, Unreal Engine games look at epic quality as being a view distance scale of 1, and we scale down from there. This was creating some unpredictable culling results where objects would disappear that would reveal a player who was hiding behind them. So we switched to saying that low quality is a value of 1 and scale up from there. So when artists are tweaking culling, they basically switch to low quality mode, tweak their culling distances, and then can assume that anything on high quality just looks better. As you can see in this example, we actually cannot get away with culling a lot of objects, which Ryan will talk about later. So we reworked the cull distances for all of our objects across the project. We were culling objects aggressively that are smaller than a player. We also set decorative objects to be disabled on mobile using detail mode. In this image, you can see some of the posters and a light that's being disabled using detail mode. And we're also not able to cut a lot of objects using this categorization, but usually it's things like posters, trash on the ground, things that are very thin in the world. And then in Fortnite, all objects are placed as blueprints. So we're able to tweak these values on a per asset basis rather than having to dig into the level and tweak every single placed object. For environment model optimization, our models have about 3 to 4 LODs, depending upon how complex that model is. Sometimes the min LOD for mobile is set to 1, sometimes it's set to 2 for objects like vehicles that are very high poly in LOD 0. We had to be extremely aggressive with our environment LODs. Here you can see for objects that are super granular, like bales of hay or things that are just repeating a lot in the world, we had to have LODs that were in the range of 20 triangles. We also had to combine meshes together. Here you can see the ground, which is not destructible, and normally it's made of a lot of different tiles, and we decided to start grouping those meshes together and rendering them as one object. We had to balance this against memory usage. Ideally, we could merge as many objects as possible to make really big meshes that render in one draw call. The downside with that is that creates a very heavy mesh that takes up a lot of memory. So we were constantly having to balance our desire for lower draw calls with not exploding our memory budget. One of the biggest optimizations we were able to make for console 60 and for mobile was to do an optimization pass on our grass. We added LODs to the meshes being used, and then we optimized the vertex shader. The vertex shader had a couple features in it, like blowing wind and being pressed down when a player steps on it. These were both being implemented using rotations, and rotations can be mathematically expensive. We simply re-implemented those visuals using translations. So as an example, when a player steps on the grass, it simply skews away from them rather than the blade actually bending. We also utilized density scale for our grass. To do this, we had to be able to tag certain types of grass to not be density scaled. As you can see, our bushes on the terrain that players can hide in are used placing the grass system. So we had to have the ability to tag those meshes to not be scaled away on various platforms. And once we did that, we were able to start scaling down flowers and grass per device profiles. In Fortnite, players can place their own walls. We call these player-built walls. These are implemented as each brick or each piece of wood is actually hand-modeled, and the wall is animated as it's being placed using a vertex shader, and it looks amazing. The problem is that's a fairly high poly object, and it doesn't play nicely with traditional LOD methods where you simply reduce the polygons being used. So we had to have our artists make custom LODs for these models where they're watertight models that have their own custom texture. And instead of using a vertex shader to animate them being placed, we use a masked material that reveals the model and then switches to an opaque shader once it's fully built. The storm clouds in Fortnite are built using tessellated planes in the sky that are tiling. This allows us to cull those planes, but to also have them be a decent poly count so that the vertex shader can look interesting on them. For mobile, we re-implemented this technique using just a large donut in the sky where the inner part of the donut uses a masked material. This allows us to pay the cost for overdraw of a masked material only where it's needed, which is the edge of the storm. Thanks. I'm going to hand it off to Ryan to continue talking about content optimizations.
Thanks, Jordan. Hi, my name is Ryan Brooks, and I am Principal Technical Artist at Epic Games. So I'm here to talk in a little bit more detail about some of the optimization work we did to help handle some of our worst cases in this game. So probably the biggest one was draw call optimization. So here's showing what one of the towers in Tilted Towers looks like once you kind of extract all the destructible individual pieces, showing how many there are. So a typical building had around 300 to 400 destructible pieces. In addition, all the lighting is dynamic, so there's no baking that we can do there. Tilted Towers originally had almost 2,000 draw calls just from the 15 buildings alone, and that was without shadows being enabled. And of course, we're tempted to just say, oh, let's aggressively cull things because that'll reduce it, but due to crossplay, we can't just start popping out walls where someone's hiding behind and they think they're safe, whereas like a mobile person is now able to spy them. So we couldn't use that as an option. Nick mentioned hierarchical LOD before, or HLOD for short, and we also could not use that as an option to reduce draw calls because we can't push this very low proxy mesh close to the player. There's no destruction, and the quality is just unshippable. So we had to look into something else. And we ended up going a little bit beyond hierarchical LOD and adding destructible HLOD, as Nick mentioned. So the goal here was to reduce buildings to one draw call while still showing the destruction. So in order to do this, we actually had to go in and make an additional custom LOD for every single destructible piece in the game. And that was around 500 pieces. And so before we did this, the lowest polygon LOD was probably around 1 to 200 polys for each thing. We had to get these things under 20 verts per mesh. So we couldn't even have UV splits. We had to merge UVs, have one smoothing group, use edit normals to make the mesh not look like a blobby pillow. It wasn't the funnest task, and we had to get a lot of artists to come and jump on and help out on this. In fact, one of my coworkers made a sarcastic comment of, I thought I joined Epic to be on the cutting edge when we asked him to do this, and my response was, well, the fine print said you will be cutting a lot of edges instead. So that the way that we enabled destructible HLOD, which I'll just call DHLOD for short in the slides, is by exposing a new setup asset for the LOD system for each map. This is called an HLOD setup asset, and it's basically a container for all the settings that one level will have for its LODs. And the way we added this destructible HLOD was by adding a second level to the hierarchy. So you'll see in there, we actually have 2 levels to the hierarchy, whereas before, we had 1 flat level across the board for the whole game, which means every building and point of interest like the city had a really crude proxy LED that you saw from far away while you were skydiving, but then you were always seeing real actors. So we also added the ability for this to merge the materials by making an atlas for each building. So some engineers had to do work so that the baker would know to take custom vertex painting into account, because you can't reuse 2 meshes with different vertex colors. And we did that by setting to merge materials in the merge settings on that same HLOD setup asset. So we really only had a small handful of these setup assets for each size building, 3x3s, 5x5s, because we identify Fortnite buildings by their foundation size. So for showing the destruction, this used a system a little bit similar to the character hiding system Jordan mentioned before, where we use vertex colors on the combined mesh to identify each piece with a unique index. So since buildings have more than 256 parts, which is all you can get out of a single 8-bit vertex color, we quantized this to be a 2D index, and then basically painted each piece to have a unique index. And then a texture was created for each building on loading each level, where we could store basically a white or black pixel for each building piece. So to destroy a piece, a black pixel is just written to that texture. The slides say render target here, but I was supposed to change that to a texture, because we actually did it on the texture on the CPU rather than on the GPU. And then to actually render the destruction, the vertex shader collapses the mesh, essentially reading that destruction texture using the vertex colors as if they were UVs, which is not exactly a new idea, but getting this all combined into one thing was kind of a new concept for the engine. And you can see that when everything gets kind of destroyed away in that image, the things that are left inside were not part of the medium HLOD, and we had to kind of exclude certain heavy things like cars and a lot of things inside buildings, because it would bloat up the poly count too much, increasing the memory. And also, we would get a little bit of standard occlusion culling benefits there anyways. This is showing the comparison for that building from, on the left, the original mesh, around 70,000 triangles from the previous low LODs, and then the destructible HLOD in the middle, and then the FAR proxy again on the right. So an important thing I'll iterate again here is that the proxy on the right is always loaded. So you can't just increase the quality of those across the board either, because then you increase the memory for the whole level. Whereas the destructible HLOD and the actual level, of course, are streamed based on getting close enough. And you can see there the polygon counts. The destructible HLOD is around 5,500 triangles, and that's with all those insane, every mesh there is 20 verts or a few or more, but it is just a lot of pieces. So this is showing the whole city from a vantage point before the destructible HLOD, and that was after. I'm going to show it one more time. Going back to before. Before. So the area to look to if you want to actually spot differences is around window frames. We lose some detail there, because we would have actually had to add polygons to capture that detail due to the way that Fortnite is textured. And we might try to improve that in the future by having the baker be able to translate between 2 meshes, but currently it doesn't do that. Another problem we had in this game is that there's a lot of trees, over 6,000 trees on the whole island. And previously we were just using standard LEDs for those. A tree would start up around 5,000 or 6,000 triangles, and its lowest LED was still over 1,000 in most cases. So we really wanted to go to something like billboards, where you have a card or a sprite for each tree. But because people are skydiving this game, you want it to be seamless. You don't want to see the traditional popping cards that you're probably all familiar with. So I got to work on a new system here, which was started out for some other work on the Apple AR Park demo. That was able to translate to this project pretty nicely. So the idea is that you capture an image of each tree from a bunch of different angles, spaced around 2 different types of layouts. There's hemi-octahedron and full octahedron, which you can think of as upper hemisphere and a full sphere. For Fortnite, we use the upper hemisphere only, since you never really see trees from below when you're far away. And this layout here allows you to render all these frames into a regular 2D texture grid, kind of like a flipbook or a sub-UV. And so this here on the left is demonstrating how, with all those frames, there's kind of a tessellated grid mesh that exists between them, where a vertex of each polygon is aligned with a frame center. So by figuring out which of those triangles the camera ray intersects with, you can then figure out which 3 subframes of the atlas to blend to. And that allows you to very seamlessly blend between the real tree and the billboard, or imposter, as we call them. And on the bottom, that's showing a weight function that for any single point in the triangle tells how much of each of the neighbor frames to blend. And if the camera is directly aligned with a vertex, that vertex effectively has full weight and the others have 0, crossfading as it gets to another vertex. This is a comparison of the source tree for the pine tree in Fortnite with the imposter. And it's important to point out that the imposter is actually a card around 8 polygons, since it's a quad that has the corners cut to try to reduce overdraw. There's a little bit of popping from the blending while you're really close, but at typical screen size distances, you almost can't tell. So we took this one step further and then also built the option to combine imposters into the hierarchical LOD system. So you can see here that when we're far back in selecting that swamp area, it's just one mesh, and that includes the floor, the water, and all the trees. But as we get closer, it switches to the actual actors. And you can see a very subtle dithered fade there, but it holds up pretty well, we think. So this lowered HLOD triangle count pretty significantly, but the major reason to do this was also just for visual quality. It does require a decent chunk of texture memory. For PC and console, we use one 2048 for color and alpha as a DXT5, and then a 1024, which contains the normal map, and then the depth map in the alpha. So basically 2 DXT5s for each tree. And we don't have a lot of trees. We have around 11 unique imposters, and we change the color of them using material instances where possible instead of having unique variants, because we do have a couple different color variants of these trees. So this is a comparison of one of the POIs, or points of interest in the game, the Lonely Lodge, or some people call it the Ranger Station. The original level geometry is around just shy of 400K triangles. When we first had regular HLODs, where the trees would just get simplified into the hierarchical LOD like everything else, it bloated up the complexity and the poly count of those pretty heavily. And they still didn't look very great when you skydived into them. So by making the imposters just merge directly into the HLOD, it dropped the poly count by more than half. And it also made the quality match the original much more closely. So this is a comparison of before and after switching to imposters in the HLOD. On the top right, you can see Wailing Woods was kind of a blobby mess. And then with the imposters, it looks much more defined, and you can tell what the trees are meant to look like. This saved around 180,000 triangles from the always loaded memory and around 270,000 verts, which is what we actually tend to talk about when we discuss optimization, since verts is what your things like vertex shaders actually operate on and what defines the memory cost more than triangles. And the GIF there is just showing what the transition is like as you go into the forest. The biggest thing to notice is you'll start to see the wind animation when it switches to a real tree, but that should be the most noticeable giveaway. The other thing we had to do is simplify the landscape pretty heavily. When we got the new version of Map 2.0 that had things like tilted towers and the new biomes, it doubled its layer count up to 8 or so. As of UE4 19, UE4 limited the mobile terrain layers to be 3. So we reached a compromise where the engineers expanded the mobile renderer to have no limit to the layers, but we still knew we had to simplify the material pretty heavily. On the right, I'm showing the different masks that were there previously. So all the black and white ones are hand-painted masks that a level designer went in and painted on the terrain. The 3 biomes up top, forest, gravel, mud, roads. And then this nice colorful thing at the bottom there is a cavity map that one of our level designers, Stu Fitzsimmons, made in Substance Designer. And that gives the whole terrain a little bit of more macro, detailed, kind of an artistic touch. And you see another layer was required called no topology in order to blend out that cavity map where it met up with static meshes like cliffs, because you would see a seam. So to simplify that, what we basically did is took every layer that we could and combined it into one texture, which we refer to as the combined color map. That was done using a combination of a blueprint tool and a few switches inside of the material where we'd say, OK, turn this landscape, instead of rendering its high-quality PC mode, to just piping through all the color information from all the different layers. And then we capture that with the scene capture actor and render it to a texture, and then reference that in the mobile path instead. We also did a few other optimizations, such as disabling fancy height blends and extra cliff textures on low-end mobile. So that's the result. We now have 4 painted layers and 1 combined color map for the terrain. And this also applies to low-quality PC, as well as mobile. So it's another example of where we try to do things that would benefit all the platforms where it applies, rather than just doing mobile-specific optimizations. So this is a comparison of what the landscape looks like on high-end PC and console right now, 2 different views. And this is what it looks like on the low PC version and mobile permutation. So the main difference that you can see from the sky is just that I'm going to go back one more time. The gravel layer seems to get a little bit more powerful, and it grays out the terrain a little bit, and that's the result of using a standard linear blend as opposed to a height blend, just because the level designers were painting with very soft masks because they were only seeing little peaks of rocks poking through, whereas now we see the whole linear contribution, and it's something we could tweak in the future. And the last thing I'm going to talk about is some fake shadow techniques that I added to the map. This is kind of an update to an old school method where we would use blob shadows underneath objects. You know, everyone knows that from Mario. You have a nice little soft blob shadow underneath you, and that's what grounds the character. And without some sort of grounding shadow, trees kind of look like they're floating, so it helps the quality. This version was made by taking captures of each tree from 4 different angles and then converting each of those to a distance field. And since we have 4 angles, we can pack each of them into the RGBA channels of a texture. And then essentially all of those trees get atlased into one little sub-UV texture, and the different times of day are kind of encoded in those color values there. So the way that that's actually applied is that the vertex shader, or I should also say that each tree has a single little quad, which is 2 triangles underneath it. And then the vertex shader distorts that quad based on the time of day, stretching it out to be longer during dusk and dawn. And then to make the actual shadow shape match the tree, a time of day weight is calculated from the current light vector. And basically what that does is it takes a 0 to 1 input and remaps it to be a rainbow gradient. So basically on that frame on the right, if you were to give it any 0 to 1 input, you would get back that color on that rainbow gradient. And then that is able to extract the right part of the atlas, or not the atlas, the channel packing with a dot product. And the reason that that works is because you can't really blend together traditional opacity masks. Once the threshold passes one to the other, you'll just see it pop. Whereas with the distance fields, because they have a continuous gradient, they will appear to morph very smoothly for almost free in this case, because we still just have one texture lookup. So that concludes this part of our tech art talk. Thank you guys for all coming out, and really good to get to talk about Fortnite. Thank you.